Good afternoon, dear students. In the last lecture, we discussed about UV visible spectrophotometer. So, what are the different components that we discussed? What are the different components of a UV visible spectrophotometer? Number one, radiation energy source. Number two, wavelength selectors or a monochromator. Number three, the sample holding compartment which contains the sample, and then the detectors and amplification and readout. So we discussed last time up to what are the different materials or sample holding devices, that is cuvettes. Now let us discuss about the detectors that are used in UV visible spectrophotometry. Now the most detectors depend upon the photoelectric effect. Okay, where incident light liberates electrons from a metal or other material surface. External circuit collects the electrons and measures their number as current. Okay. So the incident light is converted ultimately into current. The current generated is proportional to the light intensity and hence it is a measure of it. Okay, so now what kind of a detector you require? The important requirements of a detector are high sensitivity. The detector used should be highly sensitive to allow detection of low level of radiant energy. Okay, number two, short response time. Okay, so first requirement of a detector is high sensitivity to detect even low level of radiant energy. Number two, short response time. Number three, long term stability. And number four, the electronic signal which is easily amplified to a typical readout. Okay, so these are the important requirements that a detector should possess. Now, what are the various UV visible radiation detectors that are used? Photocells, phototubes, photomultiplier tubes. Okay, photocells or barrier cells are generally used in colorimeters. Phototubes and photomultipliers are generally used in UV range of in a spectrophotometer. Okay. After a detector, there is an amplification and readout compartment. Okay. Now the radiation detectors detect the radiation, generate an electronic signal proportional to the amount of transmitted light. Okay. This signal needs to be translated into a form that can be easily interpreted. Okay. So translation of this signal into a form that can be easily interpreted is done by amplification devices, ammeters, potentiometers, and potentiometric recorders. Now, the common type of detectors, as I told you, are photocells or photovoltaic cells or barrier cells. Then we have photo multiplier tubes, right? Now let us discuss various detection devices used in UV visible spectrophotometer. The first and foremost is a photocell or a barrier cell that is commonly used in a colorimeter. The photocells are made up of either cadmium sulfide or silicon or selenium, right? Uh, Out of the three, photocells are either made up of cadmium sulfide or silicon or selenium. Selenium photocells are the most commonly used ones. What does a photocell consist of? It consists of a steel base coated with a silver film, sometimes gold also, and finally there is a thin coating of selenium. So we have a steel base or a copper base on which there is a coating of there is a selenium layer, then there is a barrier cell, and then a coating of either gold or silver. Electrons pass from selenium to silver, not in a reverse direction. Electrons pass from selenium to silver. Silver acts as a collecting electrode and steel plate acts as another electrode. Okay. So silver is the collecting electrode and steel plate acts as another electrode. So just remember, there is a steel plate which has a coating of gold or silver, mostly silver, and the silver in turn is coated with selenium. Electron pass from selenium to silver. Silver is the collecting electrode and steel plate acts as another electrode. The current flows between these two electrodes, that is between positive and negative electrode, current flows through them, and then the current that is flowing through the two electrode is measured by a microammeter. So such UV visible detectors, that is photocells, have a very long life. They are commonly used in colorimeters. So you can see here, there at the bottom there is a metal plate of iron coated with a layer of selenium, barrier cell coated with either silver or gold. Electrons flow from selenium to silver. So at the bottom there is iron which acts as a positive electrode and silver which acts as a negative electrode. Silver is the collecting electrode. The second type of detectors that are commonly used in a UV spectrophotometer are phototubes. Okay, phototubes consist of a glass envelope. It consists of a glass tube with a quartz window, and there is a centrally placed metal wire which acts as anode, and there is a semicircle plate which acts as cathode, which is coated with alkali or alkaline earth metals, right? So there is a glass envelope having a quartz window. Through the quartz window, the radiation will come inside. There is a centrally placed metal wire which acts as anode, and there is a semicircle plate which acts as cathode. The whole thing is coated with alkali or alkali earth metals. The energy of the photon is transferred to the loosely bound electrons of the cathode. See, the electrons first pass, or the radiation light passes through the quartz window, reaches the semicircle cathode. Energy of the photon is transmitted to the loosely bound electron of the cathode. Electrons excited move towards anode. Okay, they move towards anode, which is the anode is a metal wire that is centrally situated in the glass tube. Okay, the electron excited move towards anode, causing the flow of current into the circuit. Right. Phototube currents are very small and they require amplification. So we need an amplifier along with the phototube, and then it can be recorded. Okay, so this is how a phototube looks like. So it consists of a evacuated glass. Okay, it consists of an evacuated glass tube having a quartz window. Right. Inside there is a metal wire which acts as anode, and you can see a semicircle plate which acts as cathode. Okay. Cathode surfaces are composed of materials that readily give up electrons, like alkali metals or alkaline earth metals. So you can say semicircle plate is coated with alkali metals or alkaline earth metals. Electrons are first, photon energy of photon is falls on the cathode. It excites the electrons, which then pass to the anode, completing the current, which can be generated, which can be you can say actually measured by a ammeter. So electrons contained in the cathode are released as photons with a sufficient energy strike the surface. This causes electrons to move through the low pressure gap to the anode, which produces a current. The amount of current is proportional to the light intensity, but here current generated is very small and hence it needs to be amplified and then recorded. So amplification and readout is necessary. The third type is photomultiplier. Photomultipliers are designed to amplify the initial photoelectric effect. Okay, so they are very suitable for use at low light intensities also. Even if a low amount of light falls on the cathode, okay, it can measure. The instrument can measure very low level of light also, or very low intensity light also, because the instrument is designed to amplify the initial photoelectric effect. Okay, so it's very suitable for use at low light intensities also. So this instrument consists of an evacuated glass tube, okay, into which sealed cathode and anode are present. Okay, at one end there is cathode, at another one there is anode, and in between the cathode and anode there are intervening electrodes. There are multiple number of electrodes which are known as dinodes. Okay, so the photomultiplier tube is designed to multiply or amplify the initial current. Hence, it is suitable for measurement of light having very low intensities. It consists of an evacuated tube having cathode at one end and anode at one end. Between the cathode and anode, there are intervening electrodes, a multiple number of intervening intermediate electrodes, which are called as diodes. So, as the light or the radiation first strikes the cathode, electrons are liberated and a potential difference is applied. We apply electric current. Okay, the applied potential difference accelerates the electrons generated at the cathode towards the first dynode. Okay, and then it is amplified, right? Then from the first dynode, the excited electron reach the second dynode. Again, it is amplified. Then it reaches the third dynode. So, at each successive dynode, higher electrical potential is applied and it acts as an amplifier. So, as the electron first strikes the cathode, okay, it is excited and then a potential difference applied accelerates the electron towards the first dynode where it is amplified, then to the second dynode where again a potential difference of a higher potential difference is applied, it again amplifies the electrons, and as by the time the excited electrons reach the anode, okay, it is greatly amplified. So you can see here there is a photocathode at the left end and anode at the right end. Okay, anode is the collecting electrode. The electron or the radiation first strikes the photocathode. Okay, because a potential difference is applied, excited electron reaches the first dynode, then the second dynode, then the third dynode, then the fourth dynode, and with the help of the diagram you can see it is getting amplified at each step, and then finally it reaches the anode, and by the time it reaches the anode the current is already greatly amplified. uh, Actually it is designed to measure low light intensities, and if the initial light intensity is high, okay, it may not be suitable, it may not be sensitive, but still they are of great choice. Photomultipliers are of first choice to be used in UV spectrophotometers. The another type of detectors used are photodiodes. They are semiconductors that change their charged voltage upon being struck by a radiation. The voltage is converted into current and it can be measured. So these are the various kind of detectors that are used in UV visible spectrophotometer. Now let us discuss about the differences between a calorimeter and a spectrophotometer. See, calorimeters are designed to operate in visible range only. Okay, calorimeters are designed to operate in visible range only, whereas spectrophotometers are designed to measure wavelength. They can use wavelengths in UV range, UV visible range, or IR range also. The radiation energy source used in a calorimeter is a tungsten filament lamp usually, whereas the radiant energy source in a spectrophotometer is a hydrogen or a deuterium lamp. If you look at the optical system of a calorimeter, the optical system or the monochromator consists of tinted glass filters in a calorimeter. So glass filters are used in calorimeters, which are the wavelength selectors or monochromators, whereas in a spectrophotometer, the monochromator consists of a prism or a diffraction grating. The material that is used for optical system in a calorimeter is made up of usually glass, whereas in a spectrophotometer, the optical system is made up of quartz or fused silica. The sample holding devices or cuvettes in a calorimeter are round cells made up of glass. Okay, the cuvette or the sample holding devices in a calorimeter is a round bottom tube or a made up of glass. In a spectrophotometer, the sample holder or the cuvette is a rectangular cell made up of quartz or fused silica. Okay, so it's a rectangular cuvette made up of quartz or fused silica. As far as detectors are concerned, the most common type of detectors used in calorimeters are photovoltaic cells. The most common type of detectors used in spectrophotometers are photomultipliers. Okay, so that is the basic difference between a colorimeter and a spectrophotometer. Now let us discuss the applications of UV visible spectrophotometry. Now, it is helpful in showing, telling us the relationship between different groups. It is useful in detecting the conjugation of the compounds. Okay. The first important is qualitative analysis. Okay, the first application of UV visible spectrophotometer is the qualitative analysis. See, the UV or visible absorption spectra is a very characteristic feature of any compound, okay, and which absorbs UV radiation or visible radiation. So the absorption spectra of a particular compound is a characteristic of that compound, and hence the UV spectrum or absorption spectrum of a compound helps in the identification of the compound, whether it is present or not. So qualitative analysis of a compound can be done by studying the UV absorption spectra of that compound, which is a characteristic of that compound, and identification is done by comparing the absorption spectra of known compounds. We already have some known absorption spectra, and the absorption spectra of unknown compound compared with the known compound, and you can find out whether the particular compound you are expecting is present or not. So it helps in qualitative analysis. So the absorption spectra, the typical absorption spectra of a compound, helps you in the identification of the compound. It is also useful in quantitative analysis. How we can do quantitative analysis? By you applying Beer's law. We'll come to that. Okay. Now, the UV visible spectroscopy is helpful in determination of cis-trans isomerism. Okay, it is useful in determination of cis-trans isomerism. Whether the isomer is a cis isomer or it is a trans isomer can be detected by studying the UV spectrum of that compound. UV visible spectrum of the UV spectrum of the compound. For example, geometrical isomers, that is cis and trans isomers. The trans isomer exhibits lambda max at slightly longer wavelength. Okay, so the trans isomer is an elongated isomer as compared to the cis isomer. The trans isomer is an elongated isomer, and hence it has lambda max. The maximum amount of light it absorbs, that is lambda max, is at a slightly higher, longer wavelength than that of cis isomer. So cis isomer will have an absorption maxima at lower wavelength, and trans isomer will have absorption maxima at a longer wavelength. Okay, so by looking at the extinction coefficient, by looking at the absorption spectra, you will come to know whether it is a cis isomer or a trans isomer. Again, I tell you, trans isomer absorbs at a slightly longer wavelength. It has absorption maxima at a slightly longer wavelength. Right. We can UV visible spectroscopy is also helpful in detection of functional group of the enzyme. So it is possible to detect the presence of certain functional group by studying the UV spectrum. Okay. Every functional group absorbs at one particular wavelength. So by looking or by studying the UV spectrum, you can determine which functional group is present in the compound. Okay. Then it also helps you in detection of impurities. Right. Say for example, UV absorption spectrophotometer of one compound. Say for example, if your compound is contaminated with any, say for example, carbon disulfide impurity is present in carbon tetrachloride. Okay, so we can measure the absorbance at 380 nanometer and check whether carbon disulfide is present in carbon tetrachloride as impurity or not. Okay, so if you study the spectrum and if you get two peaks, that means it is contaminated with or the compound is impure. Right. Similarly, benzene impurity in alcohol can also be determined. Alcohol absorbs at 210 nanometer. And if you get absorbance at 255 nanometer or so, but at other wavelength also, then that means what? The alcohol is impure. Okay, so benzene impurity is usually present in alcohol. So if you get absorbance only at 210 nanometer, alcohol is present. If you get absorbance at some other wavelength also, that means impurity is present. So like that, carbon disulfide impurity in carbon tetrachloride can be determined. At the same time, the impurity of the impurity in alcohol, which is generally benzene. So benzene impurity in alcohol can also be determined by studying the absorption spectrum. Okay. Now the next is, see, we can also study various physico-chemical properties of a compound. Various physico-chemical properties of a compound, like see, dissociation constant, association constants. Okay. The various physical phenomena like heat of formation of a molecular addition compound or complexes in a solution, determination of empirical formulas, hydration equilibrias, then association and dissociation constant of acid and bases, determination of intermediates can also be done by with the help of UV visible spectrophotometric analysis. As I told you, purification monitoring can be done. Whether the compound is contaminated, whether it is pure or impure, can be checked by studying the spectrophotometric analysis. Okay, by detected by spectrophotometric studies. For example, as I told you, carbon disulfide impurity in carbon tetrachloride can be determined by measuring the absorbance at 318 nanometer. At 318 nanometer, only carbon disulfide will absorb. Okay, benzene impurity in absolute alcohol can be detected by measuring the absorbance at 280 nanometer. Okay, alcohol does not absorb at 280 nanometer. Okay, then molecular weight determination. A UV visible spectrophotometer can also be used for determination of molecular weight of a compound. Again, that depends upon absorption spectra. Right. Then it also there are other applications like structure determination, then kinetic studies like chemical kinetics, analysis of inorganic compounds, measuring the concentration of solution, absorbance band is used to measure the concentration of a compound. Okay. Then qualitative analysis, as I told you, quantitative analysis. Okay. As far as quantitative analysis is concerned, what is the concentration of compound can be determined by using the Beer's law. Okay. This we have discussed also earlier. So as far as determining the concentration of a compound, that is quantitative analysis is concerned, we prepare a standard graph where the known concentration of the compounds are taken, their absorbance is measured, and the absorbance of the unknown compound is measured, and we plot a graph of absorbance versus concentration. Okay, when you plot a graph of absorbance versus concentration, you get a straight line, standard graph. Okay, and then you plot, okay, you mark the absorbance of the unknown compound on y-axis. Okay, you mark the absorbance of unknown compound on y-axis, extrapolate it on the standard graph, and extrapolate that point on the x-axis, and the point where it meets the x-axis is the concentration of the unknown compound. So quantitative estimation, that is concentration of unknown compound, can also be calculated with the help of a UV visible spectrophotometer by using Beer's law. Okay, so these are the various applications of UV visible spectrophotometer. So what are the application? Qualitative analysis, quantitative analysis, then cis-trans isomer, geometrical isomer determination, then various physico-chemical properties, purification monitoring, molecular weight determination, and so on. So that's all about the UV visible spectrophotometer. So in case of UV visible spectroscopy, we have to discuss about the various components of Beer's law. We have to study the laws of absorbance, that is Beer's law. Then we have to study about the UV visible, the block designing of a UV visible spectrophotometer, the components, and then what are the applications and what is the difference between a calorimeter and a spectrophotometer. So that's all about UV visible spectroscopy.